Thanks a lot.
Thank you.
So our fifth talk is by Nick Kossifidis. Nick's currently a research engineer at ICS Forth, and Helena teed him up nicely, I think, to suggest that the topic is really mainly to do with the trusted execution environment type work that's going on within RISC-V. I hope that's right.
Yep, hello, let me share my screen. Okay, can you see it now?
Yes, we can.
Okay. I'm Nick. I'm the chair of the Trusted Execution Environment Task Group. And let's walk through what we currently have on RISC-V for memory safety to begin with. So memory safety is a priority because in order to build anything, we need memory isolation. For secure boot, for implementing other security mechanisms, this is where we should, this is what we need to have. Helena gave you an overview before. We have three privilege modes basically on RISC-V. We have machine mode, which is the most privileged mode. And there we only have physical memory addressing. We do not have an MMU for machine mode. And then we have the supervisor mode where the operating system lives and manages an MMU. And then we have the user mode where applications run. So there's also hypervisor mode, which is basically a more privileged instance of S mode. So basically we have HS mode and VS mode. HS mode is a hypervisor version of the privileged version of the S mode that can manage other guests, and the VS, it's the virtualized S mode, is where the guest would be. And in order to do that on H mode, we have the second level of translation, which I'm going to go through later on. So let's begin with when we are on M mode and we do not have an MMU there, and we want to isolate the memory of M mode from the memory of the less privileged modes, such as S and U mode. By default, M mode can access everything, and you can only restrict access to M mode using this mechanism we call physical memory protection. And the moment you have, and then M mode can allow access to S and U, because by default, the less privileged modes cannot access anything. So when you put the system, M mode can access all physical memory, and S and U, they cannot access anything. So M mode should go there and configure a set of areas where the S mode and U mode can access. So this is the kind of isolation we have right now. M mode can allow access to S and U mode that can restrict access to everybody. We cannot restrict access only to U mode and allow access to S and U mode. This is what we are trying to accomplish with an extension of PMP we're working on. So PMP, you can think of it as a firewall, basically. You have a request coming up for a specific address, and then it goes through a rule set where you basically have a set of registers describing memory regions. And from lower to higher priority, those registers are being checked for the address you just requested. So you can protect, you can have read, write, and execute permissions for different memory regions, physical memory regions. And your typical use would be that the M mode, the firmware on M mode would boot and would allow the whole, allow S mode to have read, write, execute permission on the memory it's going to use. And then S mode would come and use MMU and virtual memory to further restrict access to itself and the applications that are managed, that are running on the system. So we have various addressing modes for physical memory protection. We can go down to 4-byte regions using the natural aligned powered of 2 addressing scheme. And you can have you can have larger regions, and you can also have use 2 registers to define a memory range. You can have one register to define the beginning of the range and another to define the end. So we have a very flexible way of describing the memory regions that PMP can use. And but that's what I want to notice at this point is that we can either have a rule for allowing access to S mode or a rule to block access to everyone, including M mode. So that's what we currently have. This is on privilege spec, the current privilege spec, it's ratified. So you can use this, various projects use this for providing TE, for providing isolation from the firmware from, so that SNU cannot access the memory of the firmware, and isolate different regions while on firmware you can basically restrict access from less privileged modes. They cannot map, for example, physical memory though. So if you have a memory region that's blocked from using PMP, the S mode, the operating system cannot create a mapping for that physical region. If it creates a mapping and someone tries to access this region, it will get a fault. So virtual memory is what we have on S mode. We are now in the operating system, and the operating system has a page table, and we have and this is used. The page table is used to isolate basically applications from each other and from the operating system. To distinguish pages that belong to the user, to the application, from pages that belong to the operating system, we have the U bit on the page table entries. And by default, the operating system, the S mode, cannot execute pages that belong to the user. This is always in place. You cannot disable this behavior. And S mode can never execute pages that belong to the user. So we have the supervisor memory execution prevention always in place. We also have supervisor memory access prevention in place, meaning that by default, S mode cannot access pages that belong to the user. This enhances security because together with the execution prevention, it blocks some classes of exploits where attackers could place data or code on an application and then somehow trick the supervisor in executing and reading the data. So by default, supervisor cannot access user memory, but we have a way of disabling this for specific code paths when we want, when we are in the kernel and we want to read data from the user in a normal code path, and we can disable for a specific code segment and then enable back. So it's basically there to prevent buggy, or let's say we are trying to reduce the attack surface there. It's not, it won't solve the bug. I mean, if the kernel is compromised, you can obviously tamper with the page table and do whatever you want. But these measures are there to prevent, to reduce the attack surface. Now, also, as I mentioned, we also have the hypervisor mode, which is another instance, a more privileged instance of the supervisor mode. So we have an operating system that can also create another page table, which is the second, it's the second stage of translation for guests. So each guest can have its own page table. And on top of that, we have a second translation stage where you can when we can display a different view of the physical memory to the guests. So this way you can isolate guests from each other. So if a guest will not be able to map the physical memory of the host or of another guest. So the hypervisor extension is not there yet, but virtual memory is there. So this is mostly, we mostly have this right now on the privilege spec. The part where about the second stage of translation is part of the hypervisor spec, and we are looking for ratifying this at the end of the year. So as I mentioned, we have this issue with PMP that we are not able to, we can either block access to everybody or allow access to SNU mode. We do not have a way of blocking access only to machine mode or for allowing access to, or have a fine grain or be able to define more specific rules, more flexible for only for machine mode and only for supervisor and user mode. That's why we started this enhanced physical memory protection mechanism. And basically the first thing we want to do is to be able to define rules that apply only to M mode so that we can create this, the equivalent of memory access prevention and memory execution prevention to M mode. The attack scenario here is that someone on S mode has placed code or data somewhere, and in a way, through some bug on the firmware, has tricked the firmware to execute this code or access this data. So with the enhanced, so with a normal PMP, we can block access to if we block access to M mode, we will block access to SNU mode as well. So we're not able to limit to allow access to S mode and block it from M mode. So that's what we started with. That was the initial idea between EPMP, to be able to implement access and execution prevention from M mode to SNU mode, and from that it evolved. And we added the concept of blacklist. So as I mentioned before, machine mode can access everything and by default. And with this approach, machine mode can't access anything. It can only access specific regions that are allowed by PMP. So now now PMP can be used as a whitelist for machine mode as well. We can block access to everything and allow access to specific regions. And we also have this flexibility, because once M mode puts a rule on PMP, it can obviously remove it. So in order to avoid that, the rules that apply on machine mode are locked. So once you set the register, you cannot tamper with the register, or with the register that sets the permission, or with the registers that set the address of the region. So once you set this rule, you cannot modify it. This is a bit impractical during every boot, because you'd want to still have protection, but in order, for example, to catch bugs, but you want to be able to modify these rules until you reach the final stages of when you finish with the initialization of your firmware and you're ready to jump to the operating system. So we added some more flexibility there to cover more cases. And with this protection mechanism, we are focusing, or we're hoping to get more fine-grained security controls and better control on more flexibility, and cover more use cases for very small devices to very large devices. I'm going to come back to this, because when I mentioned small devices, now we have another extension on top of enhanced PMP for that. So memory protection unit, this is to basically, it's an alternative to virtual memory, okay? When you do not have, you have S mode in this case, but you do not want to use the MMU, or you do not have an MMU. This is, for example, this happens on IoT devices or very small devices, or you may just want to have MPU only for the second stage of translation, because you just want to isolate yes from each other and not have present them with a different, with a virtualized, let's say, physical memory. So it's straightforward. It basically follows the encoding of EPMP. We are using a table very similar to EPMP to, again, provide similar functionality to S mode this time. So we can use the MPU to isolate S mode from U mode, and various applications on U mode from each other. Lightweight TE, this is now, we are focusing, you have devices, very small devices, that they do not have supervisor mode at all. You only have machine mode and user mode. And in this case, we'll end up running multiple things on machine mode that are privileged. So you have your firmware, and you may have an operating system, you may have a service there, a trusted service. And right now, even with the enhanced PMP, we do not have the capability of isolating things inside M mode. So you either have everything on M mode is one context, and the firmware, for example, can see the memory of the OS, and the OS can see the memory of the firmware and the service, and they can tamper with data there. So we want on systems that they do not have S mode to have another privilege mode for controlling access via virtual machine, via virtual memory, or the MPU. We want to be able to have better isolation within M mode. So we define the secondary context within M mode, and we extended the EPMP to be able to define rules that apply only to that secondary context. And those rules are locked, but they are so the secondary context cannot modify them, but the primary context where the firmware runs can modify them. So you can use the firmware to context switch also between the various things that are running on secondary context. So you may have your firmware, it will be isolated from the OS, and when you want to switch to a service running on the secondary context, you go to the firmware, and the firmware will swap those rules on PMP that are editable to allow access to the memory of the service. This is under development. We are looking for this to be frozen by the end of the year. IOPMP, this is basically physical memory protection for devices. Okay, we want to be able to prevent devices from accessing memory, protected memory. So, okay, you have PMP that blocks your CPU from accessing a specific region, but your GPU, for example, or a DMA engine can access this. So we want to have this mechanism for basically, you can think of it as a subset of an IMMU to restrict access to the device from the device to the memory. So the device cannot, we are protecting the memory from the CPU, from other cards, for example, other threads, and we can also use IOPMP to prevent access from the device to the same memory. So that's all with memory safety. We also have some other mechanisms in place. Pointer masking is an interesting one. Pointer masking can also be thought as a memory safety mechanism. Basically, the address, you request an address, and instead of accessing, before accessing the address, you mask it with a mask, and then or with a base register. So this way, the hardware will ignore the bits of the address that are in the mask and will replace them with the bits in the base register. This is very useful for many things. For example, dynamically compiled virtual machines, Java, VM, and dynamically compiled languages can use this for tracking ownership of memory, and they can use this for the garbage collector and all sorts of stuff. It's basically a way of memory tagging, but it's not done by the hardware. The hardware does not check the tags. The hardware ignores the tags and that are placed on the bits that are masked of the address, and then the software is there to check them. So it can be used as a memory tagging, software-based memory tagging mechanism, but it can also be used for restricting access to, for example, when you're running inside a library, when you're jumping in the library itself can set the mask register so that any calls that are outside the range of the library are ignored. So, or caught, okay? So you have, for example, you're jumping to a library that only wants, that you want the library to prevent any calls to code that's outside of the library. You can use memory masking to limit the range of addresses the library can call or access in general. Control flow integrity. Well, you've probably heard of other architectures doing similar things. We want to protect the control flow of the program, meaning that an attacker will not be able to tamper with the return address or jump somewhere else. So we have backwards protection using a shadow stack. So every time you return from a call, you check the shadow stack to see if the return address is there. If you are called from a function, you're only able to return back to that function. You're not able to return somewhere else. And we also have forward edge protection, which means that you are only able, from one function, you are able to jump to other functions using labels. So this is another novelty, let's say, because right now there is a similar mechanism that you can declare call sites so that these are places that you are allowed to jump to. But in our case, because we use labels, you're also checking that you came from the right function. So we're not just checking that we landed on a valid landing point, but we are also checking that we came to that landing point with a valid label. So it's very interesting. It's in very early stages of development, but we hope we will have something more concrete, let's say, by the end of the year. I don't think we'll freeze this anytime soon. I believe we're looking next year for freezing this. Other proposals in progress. So we have what Ronan mentioned previously, when we are working on FenceT, or security flash, which is basically the flash everything approach Ronan mentioned. this started from cash management operations, and it ended up being a separate discussion. We haven't reached consensus on that. Basically, because of the question I asked previously about the speculative execution. So it's not easy to just use this approach when you have out-of-order cores. And we are looking for ways to make this look clean and do the job. So secure function calling, this is another thing we are talking about. Basically, we want to be able to switch to and from a trusted environment in another context without going through M mode. So when you want, the concept here is that we have PMP limiting access to the physical memory of a process, and when we want to call that process, we need to go through the firmware, so that the firmware will allow us access to the physical memory. So we're looking for a way to accelerating this, so that we can have we can call something on this secured area without going through the context switch and everything. We want to make it a faster way of jumping in and out of enclaves, basically. So that's all. I hope I'm on time. So please let me know if you have any questions.
Yeah, that's great. Thanks a lot, Nick, for the overview. It's quite a lot to pack into 20 minutes, I realise, so we give you a hard task in that respect, so thanks a lot. So we do have a couple of minutes for questions for sure, if there are any. If there aren't any questions, because we've had a pretty long session, I'm tempted to say we just move on to the final talk. Oh, there we go. Is there any relationship between your task force and the Keystone Enclave?
Okay, so we've worked with various groups that have done enclaves. We've worked with RISC-V when they created multi-zone, and we've worked with Keystone Enclave with Keystone people as well. Keystone is a software-based. It's a software implementation, so it relies on it relies on what we have right now. They can do what they want with PMP, but with EPMP they have more flexibility, so that Keystone will use EPMP at some point. But I don't know if they will be using the MPU or the other, or lightweight T, for example. But remember that we are talking about hardware mechanisms here. We're not talking about software implementations, or how would you, for example, OPTE, the global platform spec, can also run on RISC-V right now, just using the PMP. So what we want is to create mechanisms for others to use, for the software to use. We're not looking to create a spec that covers both hardware and software. But yeah, we are in contact with Keystone, with RISC-V, with global platform, with anyone that, because we want to know what they need in hardware.
Okay, so thanks again, Nick.
Okay, thank you. Please feel free to reach out and join our group, and because we are changing a bit the organization now. We will have multiple task groups for each one of the tasks that I mentioned. It is going to become a separate task group. So feel free to join, and we need more people. And this is an ongoing process, and it's really interesting for those in the security domain. So see you around.
Great, thanks.